Welcome to Math with Professor V. This is video lecture for section 3.3 for differential equations on applications of nonlinear equations. Now, previously we've looked at applications involving linear differential equations. Particularly, we found the law of uninhibited growth to model population growth and decay, as well as Newton's law of cooling. But we know that it's not realistic for a population to grow in an uninhibited fashion forever, right? If we think about it, a population will often increase exponentially in the early stages, and then it levels off and approaches what we call the carrying capacity. And this is because of limited resources, right? You have constraints due to size, geographic constraints, you have limitations on resources such as food, water, etc. So here's basically how we come up with now the logistic model, which is going to account for this leveling off, basically. So say P of t is the size of the population at time t. And we assume that the rate of change of the population is equal to some constant times the size of the population. This is what we looked at in the previous lesson. This holds, this is approximately true as long as P is small. Basically, again, to summarize, the growth rate, this is the growth rate, is initially close to being proportional to size. Now, in other words, the relative growth rate is almost constant when the population is small. The relative growth rate is the quantity dp dt divided by p relative to the size of the population. And it's almost constant when our population is small. But what we want to do now is make our model more precise. And so we want to reflect the fact that the relative growth rate decreases as the population p increases, and it does become negative if P ever exceeds its carrying capacity, which we'll call M. Okay, so the growth rate can start to become negative, decrease. The population will decrease if for some reason the population exceeds the carrying capacity. M is what we're calling the carrying capacity. It's the maximum population that the environment is capable of sustaining in the long run. You won't have to come up with that. In practice, yes, you would, but for all of the applications that we're going to be solving, that's going to be given to us, okay? That would take extensive research. So the simplest expression for the relative growth rate that incorporates these assumptions is the following. So here's the relative growth rate, right? I wrote it over here, dp dt divided by p is equal to some constant k times 1 minus the population divided by the carrying capacity. And then from here, what we do is we multiply both sides by p, and that way I've isolated now dp dt, and this is the logistic differential equation. We're going to solve it. Oh, yes, we are, because we know how to solve a good little variety of differential equations up to this point. Notice this differential equation here is separable, so we can solve it explicitly, and let's do so. I'm going to move dt over to the other side. All right, so we have dp, let me rewrite the OG first, dt equals kp times 1 minus p over m. Now, all of these terms, these are a function of p. M is just a constant, k is just a constant, so I'm going to move them over to the left along with dp, and then dt gets moved over there. So now I have 1 over p times 1 minus p over m dp equals k dt. All right, and then our job is we need to integrate both sides. The right-hand side looks like a walk in the park. Left-hand side, a little spicier. Why don't we clean it up a bit, and then hopefully things will reveal themselves to you. I'm not going to write out the integral. I'm just going to do some basic algebra. Clean up. This is a complex fraction. I don't love that. So let's multiply everybody by m first. And then now look, we have m over. Now this m will only distribute here and here. If you distribute it to the p as well, now you really truly multiplied by m squared. So just hold yourself accountable. P times m minus p. Good? All right, m is just a constant. Why don't we go ahead, find the partial fraction decomposition for this expression. P and m minus p are both linear factors. So here's the setup. We'll have m over p times m minus p equals a over p plus b over m minus p. Multiply through by the LCD, multiply through by p m minus p. And we have m equals a times m minus p plus bp. Okay, so let's say p is equal to m. Then I have m equals a times 0 plus b times m. So b is 1. And then say p is equal to 0. Then I have m equals a times m plus 0. And I get a is equal to 1 as well. Okay, so now let's put everything together. Originally we had integral. And using my decomposition, this is 1, this is 1. So I'm just going to have 1 over p plus 1 over m minus p dp equals integral k dt. Fun? I love it. That worked out so nicely. Okay, now let's antidifferentiate throughout the equation. So antiderivative of 1 over p is going to be ln absolute value of p. Be careful, I'm not going to actually use sub here, but because there's a minus sign in front of that p, the antiderivative is going to be negative ln absolute value m minus p, okay, equals antiderivative of k with respect to t is kt plus, I'm going to put c. All right, let's clean up, see if we can isolate p. And I have news for you, we certainly can. So using our log properties, let's combine. Left-hand side is going to be natural log absolute value, p over m minus p equals kt plus c. And then what I'm going to do is flip the argument inside my natural log, which is the same as adding an exponent of -1 here. And when I do that, remember from our properties of logarithms, that's multiplying the logarithm by -1. So I'm going to basically hit everybody in the equation with a -1. And then the left-hand side will become natural log absolute value m minus p over p equals negative kt minus c. All right? Yeah, that minus has to go throughout. And then from here, I'm going to take e, raise it to both sides. Hold on, that is so crooked. Excuse me. Okay. E raised to the left-hand side, e raised to the right-hand side. So then now where are we at? Then we have absolute value m minus p over p equals e to the negative kt times e to the negative c. Okay. And then let's clean up in here. I have absolute value m over p minus 1 equals e to the negative c times e to the negative kt. And then if I drop the absolute value bars, what does that do? Well, we have to put plus or minus on the other side of the equation. So plus or minus e to the negative c, e to the negative kt. And then why don't we go ahead, redefine that right now. Let's say let a equal plus or minus e to the negative c. That way things start looking better. And then we're almost done. So m over p equals 1 plus a e to the negative kt. Let's take the reciprocal of both sides. So p over m equals 1 over 1 plus a e to the negative kt. And then multiply by m. P is m over 1 plus a e to the negative kt. And there is our logistic growth equation. Woohoo! All right, so m will be given to you. All right, now a, what is a? We find a by putting t equals 0 into equation 6 from earlier. So if t is equal to 0, then p is equal to p naught, which is the initial population. And so we have m minus p naught over P naught is equal to A times e to the 0. And that's just going to be A. And then if we want to put it all together, we can say our solution to the logistic equation is as follows. P of t equals m over 1 plus, let's leave it as A, e to the negative kt. This is the solution. And then just off to the side, we'll specify where A equals m minus P naught over P naught. And those will be given to you typically, okay? Now, using the expression for P of t in equation 7, this is the 7th equation, we see that if you take the limit as t approaches infinity of P of t, so let's think about this. As t is getting large, this exponent is getting very, very large in the negative direction. So e raised to a very negative number is going to approach 0. So then we're just going to have m over 1 plus 0. That limit is going to be m, which is what we expect. We said that the carrying capacity m is the max population that can be sustained long term. All right, beautiful. So I believe this logistic equation. Do you? Let's do some examples. You'll need a calculator. And here we go. Write the solution of the initial value problem. dp dt equals 0.08p times 1 minus p over 1,000. And then here's the initial population. P of 0 is 100. And then use it to find the population sizes P of 40 and P of 80. At what time does the population reach 900? Now, you don't need to rederive what we just did, okay? You can use the results, and hopefully you recognize the form. This is Kp times 1 minus P over M. So I'm looking at this initial value problem, this differential equation, and I go, oh, this is the differential equation whose solution is the logistic equation. So I'm not going to go through the process. I'm just going to bust out the logistic equation and identify all of the relative components, okay? Logistic equation with K is right here, 0.08. And then M, can you identify M? Very good, it's right there, it's 1,000. And then P naught, my initial population, 100. Bravo. Okay, let's find A, because remember, A is a part of our solution. So A is M minus P naught over P naught. So that's going to be 1,000 minus 100 divided by 100. So that's 900 divided by 100, 9. Look what lovely numbers. Okay, so putting it all together, then P of t is going to be M over 1 plus A e to the negative kt. How are we doing? Nice, right? It's a nice little equation. Okay, what else do they want from us, these people? They said find population sizes P of 40 and P of 80. So I'll just substitute those values in for t. And then at the end, what time does the population reach 900? We'll set it equal to 900. Got it. Here we go. So P of 40 is going to be 1,000 divided by 1 plus 9 e to the negative 0.08 times 40. And then just use your calculator. Okay. I did write it out one more step in case you don't have a calculator. You could do 1,000 over 1 plus 9 e to the negative 3.2. But then at that point, you're done, right? Okay, and this is approximately 731.6, which is rounding to 1 decimal place. I think that's what the back of the book did. And then P of 80, similarly, 1,000 over 1 plus 9, e to the negative 6.4. Just double that exponent now. And that's approximately 985.3. Okay. And then at what time does the population reach 900? Now I'm going to set everything equal to 900. So that equals 1,000 over 1 plus 9 e to the negative 0.08 t. So now to solve, I did a cute little shortcut situation. Are you ready for it? Okay, this is over 1. I took the reciprocal of both sides. So this is 1 over 900 equals 1 plus 9e to the negative 0.08t over 1,000, but I didn't even write that. I just savagely went in and said, oh, that means there's going to be 1,000 up here. I know. And then I reduced that to 10 over 9. So that's 10 over 9. And then if we subtract 1, which is 9 over 9, yes, then I have 1/9 equals 9e to the negative 0.08t. So that's 1 over 81. E to the negative 0.08t equals 1 over 81. And then take the natural log of both sides. So negative 0.08t equals natural log of 1 over 81, which is the same as negative natural log 81. Then my negatives cancel out. So the exact answer would be t equals natural log of 81 over 0.08. And that would be how you would be expected to give it on an exam. Did they give me units of any kind? No. Okay. If you put this in your calculator, it's about 54.9, which I believe the back of the book rounded to 55. I'll say years, but they didn't really specify. So I won't write it down. I just said it. I won't write it. Okay, good. All right. I have another example for you, and then like a little application. So good stuff. When I first learned about this model, I was fascinated because it did always bother me, exponential growth and decay. You know, I was like, it can't go on forever. Certainly not. All right. Assume that the carrying capacity for the U.S. population is 800 million. Use it and the fact that the population was 282 million in 2000 to formulate a logistic model for the U.S. population. All right, so let's let t equals 0 correspond to the year 2000 for simplicity, okay? And we're assuming logistic model, so let's find A. A is equal to m minus p naught over p naught. In this case, P naught, initial population, is going to be population in the year 2000. And M, the carrying capacity, was given 800 million. So this is going to be 800 minus 282 over 282, which is 259 over 141. Okay, and there's no units on A, because these are in millions of people, it cancels out. All right, putting it together, P of t is m over 1 plus a e to the negative kt. So m is 800. This is all in millions. Over 1 plus 259 over 141 e to the negative kt. And let's just remind the people, P is in millions. So no, I can't find K. They didn't give me enough information. I just wrote out, the model, but I need more information if I'm going to pin down exactly what the value of K is. They'd need to give me something like this. So determine the value of K in your model by using the fact that the population in 2010 was 309 million. So this corresponds to t equaling 10, and then this tells me P of 10 is 309 million, but who wants to write an extra 6 zeros for no reason? Not me. All right, so 309 set it equal to 800 over 1 plus 259 over 141 e to the negative k times 10, okay? Beautiful. Then you're going to do the little switcheroo. Remember, we take the reciprocal of both sides, and I'm also going to multiply the 800 over simultaneously. You guys are in differential equations. You should be able to handle algebra like this. It should not be traumatizing. It should excite you. So 800 over 309 equals 1 plus 259 over 141 e to the negative 10k. Subtracting 1 is subtracting 309 over 309. So we've got 491 over 309 equals 259 over 141 e to the negative 10k. Get rid of that coefficient. So multiply both sides over here by the reciprocal. 141 over 259. 141 over 259. Boom, 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 boom. So then I have over here e to the negative 10k equals, I'm just going to carry on with no calculator for a minute. 141 times 491 over 259 times 309. Then we'll take the natural log of both sides. So then we have negative 10k equals natural log 141 times 491 over 259 times 309. Remember what I did to get rid of the minus sign? You have 10k equals, flip the argument. So 259 times 309 ends up being 26,677, and then 141 times 491 is 223,077. Okay, so we're almost there. So K is 1/10 ln 26677 over 23077, which is approximately 0.0145. Okay, there we go. Beautiful. Now, use your model to predict the U.S. population in the years 2100 and 2200. So this would correspond with T is 100. This would correspond with T is 200. Okay, most of this can be done in the calculator. So P of 100 is 800 over 1 plus 259 over 141 e to the negative. I'm going to just put 100k because k is quite messy to write. And I'm going to actually use the exact version and store it in the calculator. I'm sure you all know how to do that by now. So this is approximately 559 million. And then P of 200, same thing, 800 over 1 plus 259 over 141 e to the negative 200k. And this is approximately 729 million. Okay, now obviously this model is limited because there's other factors to consider that are occurring in the US and globally that will affect the population growth. So take this with a grain of salt, you know what I mean? Just like you wouldn't trust the uninhibited growth model, the exponential model, long term, this also has its weaknesses. What is the US population though today? I'm very curious suddenly. And according to ChatGPT, as of early 2025, the United States population is estimated to be approximately 341 million people. Okay. In 2025, 341 million. Part D. Use your model to predict the year in which the U.S. population will exceed 500 million. So then you would set 500 equal to 800 over 1 plus 259 over 141 e to the negative kt. I know what k is. I just don't want to write it because it's so gross. You know what I mean? Okay, we're going to do our good old flip and switch. So we've got 800 over 500 equals 1 plus 259 over 141 e to the negative kt. 8 over 5 minus 5 over 5, that's 3 over 5 on the left-hand side, equals 259 over 141 e to the negative kt. Again, multiply by the reciprocal. So then we have 3 times 141 over 5 times 259 equals e to the negative kt. Take natural log of both sides and the reciprocal of the other side. So then we have t equals 10 natural log 423 over 1295. That's all of this being multiplied out, divided by k, which is natural log 23,077 over 26,677. Well, I flipped this to get rid of the negative, okay? And then all of this comes out to be approximately 77.18 years. So in which year will the population exceed 500 million? In the year 2077. Hopefully I'm alive and I'll tell you whether or not it's correct. You guys, I had to report back because it was killing me. I wanted to know what the population was going to be according to this model in the year 2025. And it's 351 million compared to 341 million. So overestimated by about 10 million people, but that's still not bad. Let's think why maybe the population's not growing as quickly as the model thinks. What factors could be causing that? So, you know, a lot of what mathematicians do is refine their models and say, what do I need to add to it to make it more accurate, to make it really reflect the population and how it behaves? Okay, moving on. Last example, comparison of the natural growth and logistic models. In the 1930s, the biologist G.F. Gauss conducted an experiment with the protozoan Paramecium and used a logistic equation to model his data. The table gives his daily count of the population of protozoa. So he's just observing, here are all the days every single day, and then here's all the protozoa that were observed. He estimated the initial relative growth rate to be 0.7944 and the carrying capacity to be 64. So that would be our K and M values. Find the exponential and logistic models for Gauss's data. Compare the predicted values with the observed values and comment on the fit. So we were given the relative growth rate, which would be K. That's 0.7944. And carrying capacity M is 64. We also need the initial population, which I'm just going to take from the table. Oh, there's my alarm, but I'm up. Don't worry. P naught is 2. Okay. So let's first write out, think back, our exponential uninhibited growth model. That's one that they want. They want us to do both models. The one that we learned earlier. So P of t equals P naught e to the kt. Remember that guy? Oh, good. So this is 2e to the 0.7944t. This is the exponential model. Now they also want the logistic model. Okay, fabulous. So we need to find A before we get there. So A is, remember, M minus P naught over P naught. M is 64. So 64 minus 2 divided by 2, that's 62 divided by 2, so 31. So my logistic model P of t is going to be 64 over 1 plus 31e to the negative 0.7944t. Perfect, perfect, perfect. Okay. So using these models, we have the following. I didn't want to put you through it, but you can easily generate the rest of the values. So notice here, here's the number of days. This is what was actually observed. This is what the logistic model is predicting, this one. And then the bottom row is what the exponential model is predicting here. I mean, notice initially they're pretty close, right? For the first 0, 1, 2 days. And then boom, the disparity really just unfolds from the exponential versus the logistic model, which is what we expect. Now, I have a graph here for you just to kind of help put everything together. So we notice from the table and from the graph in this figure 4 that for the first 3 or 4 days, the exponential model gives results that are comparable to those of the more sophisticated logistic model. We could see that clearly right in here. But then afterward, boom. So here's the logistic model. Here, here is the exponential model, here is the logistic model, and then these scattered dots are the actual observations. Now notice, once t is greater than or equal to 5, this exponential model is hopelessly inaccurate. Look where it's going, all the way off here, when the actual observed values are here. And the logistic model, it does fit the observations reasonably well. So what does that tell us? Well, we can improve models. And we can improve them even beyond the logistic model. We don't need to stop there. The law of natural growth and the logistic differential equation are not the only equations that have been proposed to model population growth. There are others. Two of the other models are modifications of the logistic model. Notice all of this is our logistic model. There's now an extra minus c. And this differential equation has been used to model populations that are subject to harvesting of one sort or another. So think if you have a population of fish being caught at a constant rate, this accounts for the harvesting that's occurring. And then for some species, there's a minimum population level, lowercase m, below which the species tends to become extinct. So this is the case when adults may not be able to find suitable mates because the population's too small, and then it would die off. And so such populations have been modeled by the following differential equation. So here's our logistic model, and then we add in one more factor of 1 minus that lowercase m, the minimum population level, divided by p. And this takes into account the consequences of a sparse population. And if you want to go into, some applied math research, you can look into modeling the spread of certain diseases or other sorts of things that affect us and refine those models accordingly. All right, so I hope you enjoyed this lesson. It was one of my favorites when I first learned it because I saw how beautifully mathematics can describe the world around us and how we can improve those descriptions with further study. That's it, guys. Don't forget to subscribe, give the video a thumbs up, and I will be back with more videos for differential equations. Oh, you bet. Oh, yes. Don't forget to follow me on Instagram, TikTok, Math with Professor V. Lots of fun over there, and I will be back sooner than later.